Then, okay, sorry. Now working. But anyway, let's start the symmetry problem. As you can see, this is Japanese garden and this is the Western type. But Western is like very symmetrical. It's coming from the mathematics maybe. Symmetry problem, mathematics easier. But Japanese people like not mathematics, but nature. Then the asymmetric garden is you can find. Even water flow is also different to Asian Eastern garden and the Western garden. You know, the Eastern garden is naturally water is go down, but Western garden is go up. Then the Western people don't like nature, but Eastern people like nature. Sorry. Then, but anyway, this our behavior of human is very strongly coming from philosophy or how to think or something. But anyway, let's start the symmetric problem. Here is some, it is a bit, almost 50 years ago, or 50 or 60 years ago, there are many physicists find symmetry breaking makes very special properties. For instance, the surface or interface of material, their symmetry is broken by the surface or the interface of material. These kind of matter, they show the very strange properties, physics. For instance, GMR or nonlinear optical property or anomalous magnetic anisotropy or orbital order or something. Here is one of the person, the Albert Fell. He got a Nobel Prize at 2007 in physics. Not only the physical property, if you consider this one, economy, asymmetric information makes unsymmetric feature of supply and demand. You know, the material goods price is, you can find in the balance of supply and demand. But if the situation is unsymmetric information of the goods, the price is opposite. Normally, the goods supply is bigger than the demand. The price is decreasing. But if this situation is opposite, supply is bigger and demand is smaller, but the price is increasing. This is pointed out at the 1972 by Keynes Arrow. She got a Nobel Prize, but economics. And this story is called Market for Lemon. This is lemon, is not fruit lemon. This is the United States slang of the used car. Used car price is opposite by supply and demand. This is some problem of the symmetric information problem. Here is the Professor Arrow, and I don't know who knows this guy. Somebody know this guy? It is maybe started from his mathematics. Nobody know? Oh, this is he is Leonardo Fibonacci. He is living in 11 and or 12 centuries in Italy, mathematician, and he find Fibonacci series by thinking of the number of rabbits and the baby of rabbits. And nowadays, many people are using this Fibonacci series for the inspection of the stock market everywhere. This is also thinking the asymmetric things. And recently, there are many people find this Fibonacci series. The first is Roger Penrose. He's a mathematician from UK, and he got the Nobel Prize Physics in 2020. It's just 3 years ago. As you know, the Penrose tile is very famous. There are no symmetry on the tile. But after Penrose, Dan Schichtman from Israel, he find the shield crystal as experimentally. This connectivity of the crystal is a non-symmetry. And he got a Nobel Prize at 2012 as a chemistry. But if you consider symmetric material or asymmetric material or antisymmetric material, it's completely different. And interesting something. This is as a introduction. This is the trajectory of the typhoon and the hurricane and the cyclones. As you can see immediately, these storms never born around the equatorial region. Why? Why the storm need just high temperature seawater? The highest temperature seawater is located here, but they are never born. The storm born just offset from the equatorial zone. They need chirality. Yeah. If the storm born, low pressure born here, they feel Coriolis force from the surface of the Earth. This force is the circulating, and there wind is go up, and the circulation. Then finally, they make a chiral helix. Chiral helix is stabilized itself, and the storm behave as a particle, but huge particle, but the particle. But the chirality is very important to stabilize as a particle. This is something similar with protected by topology and the chirality also. Then let's start the non-asymmetric matter. I'm talking to the chirality. Chirality is no symmetry. There are only one symmetric operation possible. This is E. E is the same. There are no symmetry. You know, as you know, our hand, one hand has a chiral. There are very, very interesting story about chirality. The first person thinking in the academic is Immanuel Kant. He published a book, Prolegomena. He wrote a thought experiment. And this one, if you wake up in the opposite side one day, you can leave. The door knob is opposite turn, and the door is not push but pull. Or your furniture is the opposite way. It is easy to leave, or it is difficult to leave, maybe. The other thought experiment is like this. Some angel find a cutted human hand on the road. She or he can recognize this hand is right hand or left hand. Maybe it is difficult. Angel has wings instead of hand. Then angel cannot compare with his hand or her hand on the road. Then maybe he or she can recognize this is the hand of the human, but she cannot recognize the right or left hand. Then finally, the Immanuel Kant summarize our right hand and left hand is different world, yeah, and the perpendicular world of the right hand world and the left hand world. But anyway, there are many interesting stories about this one. The other person is later person is Johann Goethe. He said in his book, the nature favors spiral, chiral spiral. The other people also find our surrounding or beings like chiral spiral. Yeah, this is the history of the all things, but this one is already told by the Professor Bart Carl is first week seminar. Then I skip. The other thing is interesting thing is this one. He is Lewis Carroll, and he's a mathematician in UK, Oxford, or Cambridge, I don't know. But anyway, he wrote a book of Alice Adventures in Wonderland. And of course, you know the story, the Alice Adventure. And he also wrote a book, the Alice Adventure in the Looking Glass. Yeah, Alice is going through the mirror, and she finds a very strange world. Is the right and the left is completely different. She wants to write a letter, but it's very difficult to write a letter, of course, inside of the mirror. And she playing this chess, but of course, this is also very difficult to play. But this is a funny story. But anyway, in this book, the Alice said the milk from the country in the mirrors taste is so bad. This is written in the 17th century, but nobody knows the chirality, even in a definition. But mathematician Lewis Carroll said the milk inside of mirror is very bad. But this is really, we already know in the next 100 years science, you know, our protein is made by the only left side protein, amino acid. They make a polymer and they make a protein. But of course, the opposite side chirality amino acid. For instance, alanine, the L-alanine is good, sweet taste, but the D-alanine is very bitter. Then if you drink milk inside of mirror, of course, the very bad taste. We know. But anyway, our life system on the earth, not only the human, but from the plant and the bacteria or wheels, even in the wheels, there are only one side amino acid and one side of sugar we have. Then there are several, the big problem of this chirality problem. This is the thalidomide. Thalidomide is a very, very good medicine for the cancer, but we have the chirality problem. They are automatically changed by our body temperature. Then this chirality thalidomide may generate, and they have the problem. But anyway, if we look at the nature, we can find a very beautiful the chirality, chiral helix everywhere. Not only the beings or life system, but from the radiation of from the nuclear is already the one side, and the molecule level, of course, and the chiral spin system is going to talk today. It is also possible to make one side. And the E1's chiral liquid crystalline is also, and bigger, we can find many chirality in the nature. The typhoon structure already I mentioned. And even maybe the spiral galaxy is possible. I don't know. But anyway, this chirality, no symmetry problem is considering in the molecular system and the chiral properties, spin system, or the phonon system, or everywhere. And the fundamental particle physics also it is possible to consider the chiral anomaly. But anyway, let's start from the definition of chirality. Chiral definition was done by Lord Kelvin. He studied in Glasgow University, and here is his name is William Thompson, his real name. But he likes River Kelvin. It's from in the just side of the Glasgow University. And then he called the Lord Kelvin. But anyway, he did the definition at the end of 18th century by the Baltimore lectures. He coined the chiral and the chirality of geometrical right hand or left hand like this. The geometrical figure is possible to change by mirror reflection. This is called chiral. Or they have the chirality. Almost 100 years later, the same university professor, Lawrence Barron, also make a definition as a motion. Yeah. If rotate right side and going front, this is the right screw. This is one chirality. The other one is left turn and go front is a left screw. If we consider only the motion, it is possible to define the chirality. This is correspond to the helicity, and geometrical chirality is so-called handedness. But today I have to go to the spin chirality. Then we have to remember the vector. You know, these are polar vector. Is if we consider the dipole of the polar vector, you can reflection by mirror is same parallel is same, but the perpendicularly is opposite. But if we consider spin system, the spin magnetic moment is axial vector. Then the parallel magnetic moment is going to opposite, but perpendicular magnetic moment doesn't change by mirror reflection. Then we have to consider this one. Then and I have to tell you the magnetic interaction of spin. You already know the hydrogen H2 made by the H atoms, two H atoms. They make a bonding molecular orbital. Bonding is lower energy than the atomic hydrogen. And they are making the anti-parallel spin system. But anti-bonding is parallel, right? Then normally the spin system getting together or closer, there naturally they make anti-ferromagnetically coupled. Yeah, for instance, this G-methylene benzene is their couple is anti-ferromagnetically, and they naturally going to the quinoid structure. But if we put the meta substituent, they are coupled ferromagnetically. Yeah, these are everything. The chemical bond we can consider, for instance, manganese and the radical, their coordination bond generate. But this case, they interact anti-ferromagnetically. But this is easy. You can find many different molecule-based magnets using this theory. Their bonding is anti-ferromagnet. It's only one consideration. You can find many different type of molecule. This study I did in the graduate school of my life. This one is 18 spins aligned, same direction, and they have the very, very huge magnetic moment value, only one molecule. This is S9. And the other system also possible to concern these couples very, very strongly by there are library, like many different. But let's see just one or several example. I already tell just before the unpaired electron is so-called organic radical can coordinate to the transition metal cation. They have the electron-rich group. Then, this case, they interact the anti-ferromagnetically. Then, but the number of spin magnetic moment is completely different. Then we can design as a ferromagnet in this case. For instance, manganese and this triplet biradical, they make a coordination compound for one dimensional. And this is the crystal structure. As you can see, this manganese is close to this manganese, the different chain. This case, these are anti-ferromagnetic couple, and this one is also anti-ferromagnetic couple. Then finally, they are going to anti-ferromagnet. But if you put bigger substituent here, for instance, bromine here, the chain just slides. And the manganese close to the radical. This case, the between chain ferromagnetically coupled. Then finally, this compound going to the ferrimagnet. But this is many, you can prepare two-dimensional magnetic material or the other one, also possible. The three-dimensional also possible to create. This one is the highest temperature magnetic transition temperature at this time, at 1995 or something. But anyway, the structure of this one is interesting. This three-dimensional and the gyroid structure. As you can see, the angle of this one is same with the thorium silicide, the gyroid. But anyway, we can make many things. And let's to consider about the chirality. of these coordination compound. Here is a one-dimensional case. We can find these chiralities same on by one chain. Two-dimensional case, their chirality is opposite. This is so-called isotactic one-dimensional chain, but this one is syngeotactic two-dimensional sheet. Then we cannot make a chiral crystal using this two-dimensional system. But three-dimensional gyroid structure is possible to one-dimensional chain is syngeotactic, but bridge is same chirality. Then if we make a bridge with a one-dimensional, it's possible to make a fully chiral enantiomeric complex. And we have to consider the spin-spin interaction between the magnetic moment. Here is already well known. The exchange interaction is already, I tell you, how the bonding orbital is coming. This one is the so-called exchange interaction. This case, spin 1 and spin 2 make a this Hamiltonian. J is a coefficient, and S1 and S2 is a magnetic moment vector. They are inner product. And then finally, we can write the cosine function of the two magnetic moment. This one is magnetic dipole-dipole interaction is also same. The exchange interaction and the magnetic dipole-dipole interaction is same. If we consider this term is cosine function. Cosine function means symmetrically by the mirror plane. Then exchange interaction, dipole interaction is symmetric for the mirror. The other one is so-called Chirality interaction. This is all the spin system. They have this interaction. Yeah, but this one is not the ground state. The excited state spin state and the ground states spin system interact to this one. This one is outer product of the two magnetic moment. Then we can consider that this one is a sine function. This is different with the previous one. Yeah, the sine function is unsymmetric by plane mirror. Then if we use this interaction, we can make a unsymmetric spin system by mirror. Then just consider this is how to the symmetric operation of mirror is going to the magnetic moment. But anyway, our three magnetic interaction, if we consider these two is cosine, is okay. Everywhere we can consider. But this DM interaction, we can consider, we have to consider the vector as a vector coefficient. It means if our crystal is centrosymmetric, this interaction disappear. Then DM interaction can work only the non-centrosymmetric crystal. Then we have to consider more the crystal space group. As you know, we have the 230 space group, and 92 is the centrosymmetric. The remain is a non-central symmetric, then possible to work the GM interaction in these space groups. But these space groups possible to make have a mirror symmetry. Then if we consider the no mirror symmetry is only the 65 space group. This is so-called chiral space group. And the remaining 73 space group, they have 1 mirror or 2 mirror. 3 mirror is impossible, but 1 or 2 mirror is possible. This is so-called polar crystal. Then in this crystal, the DM interaction possible to work, but this is a different way. Yeah, this is similar how to divide the symmetry space group. 230 central symmetric, or no, there are mirror plane inside and the each cell. This case is polar, but no mirror, so-called enantiomorphic space group. And this is the only chiral, really chiral space group or not. We can divide. These were 43 is so-called the Sonke group. And this one is already explained by the Prasabhat curve already. And the 22 space group is so-called the purely chiral space group. But this Sonke group and the chiral space group is a bit confusing. For instance, this is a P21 space group. We can consider that these are 3 different types of the point group. The space group based on the point group, there are no difference of right-handed or left-handed, just considering point. That is the confusing part. These are so-called racemic P21 group, and this one is enantiomorphic, and the random located, right and left hand, is also possible. These are all same space group, but the molecular chirality is completely different. This one, that one is racemic mixture, but this one is only the enantiomorphic. But if we consider the black and the white point, it is so-called Shubnikov space group, is possible to recognize these 2 space groups. Then if we consider the spin chirality, we have to take using the Shubnikov space group. This is so-called magnetic space group. But this is only white and black point. Black is up spin and white is a down spin. But real chiral material, they have the helix. Then we have to use the color space group, not only black and white space group. Color. Then we have the infinite of space group on this case. But anyway, during these maybe near 25 years or 30 years, we synthesize many different kind of chiral magnet. Just we get the chiral space group and put the spin and interact ferromagnetically or anti-ferromagnetically. Then we can synthesize this kind of material, chili. Almost more than 50 magnets we create from the molecule-based and metallic-based, inorganic-based, or intermetallic compound also possible. But let's see the spin structure on them. There are several types of spin system is coming from the DM interaction. Here is helical magnet, and the right helix and left helix and the right helix. This is racemic pair, and this is so-called the Yoshimori type helical magnets. And the counting, spin-counted antiferromagnet also possible to generate from the DMI interaction, but this one is only polar space group, not the chiral one. They need a mirror, at least one or two mirror. And this one is all same helix. This is a chiral helical magnetism. This one is helical magnetism, but this one is chiral helical magnetism. This one is real we want. Only one side helix structure we need. And we have to consider the more macroscopic scale or microscopic scale. As you know, the molecular level is a microscopic chirality, but crystal chirality is macroscopic chirality. Then, if we consider the spin system, this one is a macroscopic spin system. And this one is a microscopic. You already know that this defines a Berry phase or spin eyes. You already have many examples. But this case, we need this one, macroscopic and magnetic chirality system. And of course, we can expect many special physical properties on this kind of material. The one is optical, magnetic optical properties, or second harmonic generation on this kind of material, and magnet-electric coupling also possible to consider on this material, this kind of material. And the molecule-based chiral magnet, it has also the properties, special properties. One is that it's possible to design, but not molecule-based. It is difficult to design from the atomic scale, but molecular is possible and transparent for the light. Anyway, we have to, I have to. This is only one or two examples I will tell you from now. This one is magnet with chiral structure. And I already working the Chirality interaction and transparent. This one is one example. It's made by Higashikawa-kun. This one is contains copper and tungsten 5, and they make a Prussian blue analog by cyanide bridge and put the chiral ligand. And easily to 1 week, we can find the crystal. And this one is left-handed chirality. They are making two-dimensional sheet, bit complex two-dimensional sheet. Yeah, here is tungsten and copper. And we are very lucky, we can grow the crystal right hand and left-handed and the racemic one. Yeah. This one is comparing the structure of the left-handed and racemic coordination compound. If we look at the skeleton of the magnetic spins are same with left-handed and racemic, but just the difference is this ligand. Chiral ligand, left-handed ligand only, or the mixture of the right hand and left hand. But anyway, we can really compare the magnetic structure on this racemic and chiral one. This one is left-handed chiral, enantiomeric one, and this one is racemic. They are ordered at the low temperature for the antiferromagnet. This is a single molecule. magnetization by temperature. They order at 8 Kelvin. Racemic is a typical antiferromagnet or for all direction of single crystal. But left-handed material, the A-axis is the red one, and the green is the C-axis. The behavior is antiferromagnet. But only B-axis, they are going to the counted antiferromagnet. What happened? This is, if we look the field dependence of magnetization is similar, we can find the anomaly only B direction. Racemic is a typical antiferromagnet, but the chiral one is B axis is straight. Then we can consider the space group on this compound, this space group P21. Then we can consider the Chirality vector on this space group. DM interaction, this blue arrow is DM interaction, perpendicular to P21 axis, they are antiferromagnetically aligned. And parallel to P21 axis, it's ferromagnetically ordered. Not spin, this one is the DM vector, Chirality vector. Then perpendicular to B, they are going to the up, down, then spins, makes a counted antiferromagnet for B axis. But parallel to P21, 2 axis, they are ferroic order for the DM vector, then they make a helix. The final structure is like this. This is just a racemic one, but if going to chiral one, they are count to B and make a helix to B. Okay, bit complicated. But anyway, if we measure the more detailed measurement, this one is the field dependence of magnetization of left-handed, and the bottom is racemic one. If we look racemic, field increasing, and they are straightforward, the magnetization is increasing. This is pure, the antiferromagnetic pair. This is typical antiferromagnet. But if we look at the chiral one, we can find some anomaly. This is deviation of the this magnetization curve. We can find this kind of anomaly. What is this? And this anomaly can find only just below TC. But further cooling code is no anomaly. Then we make a spin Hamiltonian on this material. We have the helical spin structure. Then we can write a Hamiltonian is using the exchange and dipole interaction, already tell you. And we have the Chirality interaction is an outer product of spin. And if we apply the magnetic field perpendicular to helical axis, then we have to add the Zeeman term. Then this is not difficult changing the formula by mathematics. Then finally find that this one is make a helix. And the Zeeman term, they are going to the parallel. This case, this term, helical, chiral helix in commensurate spin structure, and this term is going to forced ferromagnetic commensurate structure. If you have the two term, incommensurate term and commensurate term, this kind of Hamiltonian must generate a solid. Then this competition makes a generate the chiral spin soliton lattice easily. And we can make or calculate magnetization by field. Then this is a plot, this Hamiltonian. This is a winding angle between two spins for B axis, this case. And the perpendicular, this one is energy. If we put the Chirality interaction is 0, this case is here and here. It's same energy, right-handed helix and left-handed helix. This is a so-called Yoshimori type helical structure. This is not chiral. They have the both. But if we put the small L value on this Hamiltonian, the energy is different. Is right-handed helix on the left-handed helix. Then finally, they are going to stabilize in the one side helix. And we also we can calculate the how long pitch of the helix by changing the Chirality interaction. You can see this is how much lattice constant we need to make a helical pitch. Here is 100 lattice constant, or several 10 times. Here the spin helix pitch is very, very long normally, by compare with crystal wind cell. Yeah, this is a cartoon to the this system. At the zero field, they make one side helix. If we apply the magnetic field perpendicular to helical axis, they generate soliton, spin soliton. Finally, they are going to forced ferromagnetic state. Then this one is the temperature dependence of magnetization, also easy to calculate using this Hamiltonian. This one is normalized by TC. At 0, 1 is the same with the TC temperature. They are increasing. At the D equals 0, they are going to just ferromagnetic state. But if they have the different D value, they drop magnetization by formation of the soliton. Yeah. Then this is a total graph, and this one is how I make. But anyway, let's go back to consider this one. Here, this anomaly is same. The temperature dependence of magnetization. They have the peak at near TC or near the saturation magnetization value. But these are data we published in 2005, is already 20 years ago. Then I have to, yeah. This is, I'll tell you later, maybe the next one. I have more 1 hour, yeah. This one is the inorganic helical chiral magnet. And in this case, the metallic magnet, then possible to measure the TEM, transmitting electron microscope. But the molecule-based insulating material is impossible, but metallic is possible. This is the measurement of Lorentz TEM. We can find the helical pitch at 0 field is 418 angstrom. It's a 10 unit cell of crystal unit cell. If we apply the magnetic field, the spacing of soliton is increasing. gradually and gradually. This is the width of the soliton here, and this one is field. Magnetic field increasing, the soliton pitch is increasing, like this. Then I already have the same. But finally, the spin structure of this, the copper and tungsten compound is racemic, is okay. It's just going to anti-ferromagnet at the 7.5 Kelvin. But left-handed or chiral one, the paramagnetic phase at order to the incommensurate chiral helical with canting for B. And the more lower temperature, they are going to commensurate chiral with canting magnet. By this is coming from the magnetic ion anisotropy. But anyway, the totally we can summarize the incommensurate spin structure and the commensurate spin structure, non-collinear chiral. They are going to the chiral helical magnetic structure by DM interaction. But at 5 Kelvin, they compete with the chiral magnetic anisotropy. Then their phase change to the incommensurate to commensurate. I have to stop anyway. Just before I'll tell you later in this one, but just 1 minute. There are many. Yeah, here is I can find. This is just a break. My brother at this winter school first week is Professor Bart, Carl, and myself. We find this account paper. This account paper was published by my boss, Yamura Sensei, and Bart Carl's boss, Misro Sensei. They are good friends at the 1980s or 70s, and they published in this paper in account chemical research in the ACS. And the title is Stereochemical Consequence of Dynamic Gearing. You know, then these are photographs of my boss and Carl's boss, Misro. And what they did at the 1970s, they mix a gear molecule by 2-tryptophan molecule, and they put some substituent here. Finally, they're possible to move as a 2 gear, but this 2 gear, we can make the chiral gear. They are moving all the time, but never go to the right side, right-handed and left-handed. You know, this is a gear, but the chiral molecule is possible. Then this one is found in a very recent review paper. It's published by Guanyu Rapin. He is also my friend. He is in NIST, Nara Advanced Institute for Science and Technology, Japanese Nara Sentan Daigaku, and he published this molecular gears. But Rapin is also an interesting person. This is work, I don't know. Guanyu Rapin is the first person to start the no work. But here is molecular nanocar race. It is this car race is doing annually in the Japan and the Toulouse University in France. Anyway, he is the person to start this gear, molecular gear cars. Okay, anyway, thank you very much. Yeah.